Somewhere in the world there's a car accident every second of every day. In Britain alone, there are tens of thousands of crashes a year. Many of these accidents break the laws of the land, but they all obey the laws of nature. It's science that can not only help save your life, but also unlock the secrets of the universe. This is a story about the law of collisions, where the police aren't the only detectives, and not all the crashes are accidents. Most of us try and avoid having a crash, but for some people, collisions aren't an accident, they're a way of life. Right now, scientists are planning the biggest crash since the Big Bang. Atomic particles will be smashed apart in unimaginably violent collisions to discover the smallest bits of nature. It's going to be the most complex and costly crash in history. Ooh, sorry.
But you're not going to see this crash on a racetrack. It's going to happen at CERN, the European Laboratory for Particle Physics, deep under the mountains near Geneva.
We are trying to find out very fundamental things. What's the universe made of, and how does it work?
If the discoveries are what we expect them to be, somebody will be getting Nobel Prizes, no doubt.
Scientists, especially physicists, have been looking for laws with a capital L, some basic principle that will tie everything together.
On this awesomely difficult journey into the unknown, the scientific detectives will rely on some simple laws of nature. The same laws of collision the police use to investigate traffic accidents.
All collisions obey the rules of nature. If police detectives know these laws, they can piece together what happened in a crash from the bits that are left. It's the same whether it's cars or atoms colliding. While the subatomic world may be strange and complex, scientists can always rely on some fundamental laws of collisions. Laws that apply from the mysterious atom to the world of the all-too-familiar.
More people are killed in road accidents than have been killed in all the wars and other types of accidents put together. We're having in excess of 1 road accident per second worldwide. In this country, we have something like 3,500 people killed every year. It's absolutely imperative that in trying to understand what's going on, that we do understand the physics. Just saying, well, I have a car and it crushes at the front and not understanding why doesn't tell me how I change things. So it is fundamental to all our work that we have to understand the laws of physics.
Accident investigation is looking at the physical evidence being left at the scene of a collision and establishing what has actually happened in the collision itself. Okay, let's have a look at the marks that we've got. I'm John Needs, and I'm an ex-police officer, and now I teach accident investigation to police officers. You can see the black marks that have been produced as the tyre has run over the surface of the road. And what that black mark is, certainly over this portion of the mark, the black mark is actually happening in the collision, what's happened to the various objects, why we have marks on the road surface, why a vehicle behaves in a particular way, and it's all based on the laws of physics.
In a skid, you may be out of control, but the laws of physics aren't. Behind the chaos and confusion of a crash is the order and certainty of nature. If you understand these rules, you can work backwards and discover just how the metal got mangled. It's over 100 years since the first person was killed in a road accident in Britain. This car may look lovely, but it's also deadly. Both car and driver would be written off in a crash.
I think that if we look at what's happened in the whole development of the cars, we can say that by understanding how energy is absorbed, this has enabled us to move forward so that in the unhappy event that you have an accident, then there's a much greater chance that you'll be protected in that accident. And without our understanding of physics, we would never have got to that place.
To unpick the chaos of a car crash, scientists need some rules they can always rely on. One thing physicists learn to bank on is the reliability of energy. Energy can't be created or destroyed. It has to go somewhere. If I don't burn off the energy in these chips, it will be stored as fat. Energy doesn't miraculously disappear. Unfortunate for slimmers, great news for scientists. They can be sure that although energy can change from one form to another, the total amount has to remain the same.
Energy is a quantity that stays the same. It can change from one form to another, but overall it stays the same. And a familiar example, if I've got this piece of snow here and I hold it above the ground and I don't let go, it's got potential energy. It's got the potential to change into motion. It turned into motion, it hit the ground. As it hit the ground, sound was emitted. So all these forms of energies were changing from one to the other, but the total of them all stayed the same throughout. And this is the principle that energy is conserved, preserved.
If we're looking at energy, we have kinetic energy if anything is moving. Of course, when two cars crash into each other, they have a lot of kinetic energy. And we have to absorb that kinetic energy in the front structure of the car. If we don't absorb it in the front structure of the car, it'll have to be absorbed somewhere, and it'll be absorbed by collapse of the passenger compartment. So we want to have the softest front structure that you can have, but would absorb sufficient impact energy. You could design a car that had its front end that would be like a spring, so that when cars collided, they crushed and then recovered. The problem there is that the cars would then bounce back. And so the change in velocity on the cars would be much greater. There's no point in stopping somebody and then saying, I'm now going to accelerate you backwards and increase your injuries. Now, you can't do that perfectly. Cars will recover, but the ideal is cars which collapse and stay collapsed.
So car designers have a stark choice. In a crash, the energy either deforms the car or the people. Energy always has to go somewhere. It can't just disappear. That's what crumple zones are about. They allow the energy to go into bending metal. The front of the car crumples, so the people don't.
The total amount of energy in the universe always remains the same. It's conserved. Nature's law on the conservation of energy is never broken. Scientists rely on it absolutely. But energy isn't the only thing that obeys a law of conservation. Motion is the key to understanding crashes. If my toy car were travelling at the same velocity as a real car, the real car would do you a lot more damage. That's because it's got more momentum. Now, momentum is the velocity of a vehicle multiplied by its mass. If two vehicles are travelling at the same velocity, the one with more mass has more momentum.
When we consider two cars hitting each other, then the first thing we have to consider is the momentum. So if you have one car that is twice the mass of the other car, then the momentum that that car has is its mass times its velocity. Both the cars are going at the same velocity, then one car has twice as much momentum as the other car. If you were to imagine something like a Mini hitting a truck, a very extreme example, you can see the very simple situation is if a truck is coming along at 30 miles an hour into a Mini at 30 miles an hour, the Mini will basically be going back at nearly 30 miles an hour. So it's had a change in velocity of something like 60 miles an hour, and the truck will be going along still at almost 30 miles an hour. So it's had a velocity change of virtually nothing.
Well, momentum is one of those fundamental features that's always conserved in every collision. The momentum is going to remain constant in a closed system. And we use that to establish, with two vehicles colliding, whatever momentum they have before the collision, exactly the same amount of momentum will come out of the collision at the other end. In fact, we use it in reverse. We know what's happened after the accident, and we use that to predict what has happened and what the speeds of the vehicles are before the accident.
Just like energy, momentum is conserved. It stays the same. In a collision, momentum has to go somewhere. You can depend on that.
The police certainly do, as they attempt to work out the cause of the accident and who's to blame from the debris that's left. Whether it's on tarmac or green bays, behind every collision are the laws of conservation of momentum and energy. It's these rules that let us predict how things behave during an impact.
When snooker balls interact, they obey the laws of momentum. Exactly the same thing happens with our cars. So the laws of momentum behave in exactly the same way with cars as with snooker balls.
Snooker is a simple example to show you've got the balls on a snooker table, and initially one of them is sitting at rest. And then the other ball comes along with a certain speed, a certain momentum, a certain amount of punch. It hits that ball, and this ball recoils. Now, if this ball comes to a stop, the ball recoils with the same momentum that this one brought in. However, this one might keep moving. And what happens to this other ball? Answer, the amount of momentum it takes is what is missing relative to what the first one brought in. And so the motion of snooker balls is actually the conservation of momentum at work. Now, whether snooker champions have that in their minds as they do the shots, I don't know, but in principle, you can work out where the balls will move based upon the conservation of momentum. And in the science of particle physics, which I am involved in, they are the very essence of the game, that we are firing subatomic particles at each other as if they were billiard balls, in a sense, and from the way that they interact with each other, bounce off each other, set each other in motion, change their form, we interpret what is going on by using the fact that the energy that we supply at the beginning must stay the same in amount throughout, though it can change from one form to another during the course of the experiment.
Whether it's snooker balls, cars or subatomic particles, if you know the momentum of any object before a collision, you can work out the direction it will go in afterwards. This allows you to look forwards so you can predict motion in the future, or just as importantly, work backwards to discover how things were moving before a collision. Whether it's a car crash or an almighty atom smash, conservation laws rule them all. Now, these rules give the crash detectives ways of understanding any collision, however messy. For scientists, physical laws provide much-needed certainty in a complicated world.
Conservation of energy, conservation of momentum actually underwrite everything that happens. There is not a single event that doesn't involve these conservations in some way or another.
The deep principle behind the conservation of momentum is that the laws of nature must be the same everywhere. So to begin with, people just noticed the amount of momentum stays constant. Oh, that's interesting. And then they found this followed from Newton's laws of motion. And then people realized that's much more general, that actually, as long as the laws of nature are the same everywhere, then momentum must be conserved.
There's one basic difference between a law of nature, whatever that might mean, and a law of the land. That if you discover something about the way that nature works, for example, the law of gravity, it's yours for all time. If you're a politician and you pass what you think is a law, the next government can change it. That's what makes science worthwhile.
Wherever we look, we find principles deep in nature that govern everything that happens in the heavens and on Earth. No wonder that pondering the universal nature of physical laws puts scientists in a philosophical mood.
What has driven the last 300 or 400 years of science is the idea that at bottom all these different kinds of phenomena, plants, colours, particles in motion, sea currents, everything, are really just aspects of matter in motion, and that matter in motion is going to be governed by some very simple laws.
I think one of the things that is very useful for a scientist and an engineer to learn is that the laws of physics apply everywhere. Whether you're dealing with cars, whether you're dealing with large bodies like asteroids hitting planets, or whether you're talking about particle physics, the laws of physics apply.
Philosophers worry about what ties things together in nature. Where does this link between cause and effect come from? Where's the cement that glues the universe together come from? Is there something more to just occurrences in space and time? Are there further links between them? And how can we conceive of that? That's a rather deep philosophical puzzle.
But while philosophers may worry where these laws come from, no one questions their effectiveness. Just outside Geneva is CERN, the European Laboratory for Particle Physics. Here, over 2,000 scientists, drawn from all corners of the globe, are using the laws of physics they know to discover the ones they don't.
If you want to know what something's made of, then break it. It's a lot harder to smash an atomic particle, but the idea is the same. Collide two particles together and look at the bits that come flying off.
At CERN, the aim is to do experiments using the smallest particles of matter, colliding them together in order to try to understand the nature of matter itself. What are we? What are we made of? What are the rules that govern the way that we and the universe is built up?
When you crash things together, you can analyze the collision using the laws of conservation. The biggest challenge to these laws is to explore nature itself on the tiniest level, inside the atom.
At CERN, they fire subatomic particles in opposite directions around an underground tunnel. These particles are then crashed together inside huge electronic detectors.
Although the interaction takes place in a very, very small space, the energies of the particles that come out, which are traveling at close to the speed of light, are very high. The momenta are very high. So to measure these with enough precision so we can reconstruct what happens in the collision requires very large detectors.
In doing experiments at CERN and interpreting them, the conservation of energy and momentum are absolutely essential. You are speeding the particles up, giving them energy of motion, and when they collide, you know that the energy that the particles had as they came together, in that moment of collision, the total energy is the same, and then after this collision, whole new forms of matter and antimatter emerge, and the energy of all those bits in total must be the same as the energy of the original colliding particles. So you can then do a balance check. You can add up all the energies, all the momenta of the various particles that are spraying out, and see if it does balance.
The particle tracks which stream out from a collision are like the skid marks in a car crash. By analysing these subatomic skid marks, you can work out what new particle, if any, you've discovered as matter breaks apart. So detectives investigating the subatomic world make sense of these patterns using the trusty rules for energy and momentum conservation.
It might seem surprising that the conservation laws apply to a whole range of events such as a car crash or collisions that occur in these detectors, but they do not seem surprising to me because I use them all the time to understand the data that comes out from the collisions in these detectors.
Scientists rely on these conservation laws today because of their triumphs in the past. One of the great success stories was the discovery of the elusive neutrino.
In the 1920s and 30s, people tried to understand the nature of what's called beta decay. We'd known that neutrons can fall apart, and they fall apart into a proton and an electron. But when they studied in detail, it seemed to be that here was a neutron, proton come out, electron come out, and sort of nothing, and it didn't seem to stack up. It wasn't balancing. And in fact, it looked like a failure of the laws of energy and momentum conservation. Wolfgang Pauli said, look, really, it's a very, very incredible idea that energy and momentum are not conserved. There must be a missing particle. And later, it was 20 years later, actually, somebody managed to detect it, but it interacts very feebly. It's very, very hard to detect. So our faith in energy and momentum conservation allowed us to infer the existence of an invisible particle.
Subatomic detective work has been successful in the past and won people Nobel Prizes. A new generation of physicists here at CERN are hoping it will work again.
They're building a new experiment. It won't be ready till 2005, and it's on an epic scale. It makes current particle physics look like child's play.
But it's got a very grown-up name, the Large Hadron Collider.
I think it's probably the biggest scientific instrument ever constructed. And it's going to collide protons head-on at the highest energies that have ever been achieved. And the idea is by colliding them with much higher energy than previously, we can smash them apart into much smaller pieces and get down to a deeper level of our understanding of the structure of matter.
By colliding the particles together at very high energy, you are recreating for a brief moment, in a very small volume, the sort of energy or temperature that was present in the real universe within a millionth of a second of the original Big Bang.
Subatomic particles will be fired around a 27-kilometer ring and then smashed into each other at almost the speed of light. Huge detectors, which act like enormous electronic eyes, will capture the results of the collision. While the existing tunnel can be reused, for the new experiment, the detectors will have to be bigger and better than anything ever built before.
One of the two detectors on the Large Hadron Collider is going to have a diameter which is about twice as big and a length which is about 3 times as big. So in volume terms, it'll be 6 to 10 times the volume of these detectors.
We've maybe got 1 billion collisions a second. And most of them are dead boring. You don't want to know. I mean, they're just glancing collisions. There's physics which we discovered, 10 years ago. Who cares anymore? What we want is the very rare case they meet head-on. That maybe only happens once a minute or maybe once an hour. When we've got the interesting things, there is a huge amount of data. The data from one of these 4 big detectors in 1 year will be about a petabyte of data. What the hell's that? If you stored it on CD-ROM, and each CD-ROM's about sort of this thick, and then you stack them up, they'll be 3 kilometers high, 1 year's worth of data. So just storing that, transmitting it, analyzing is going to be a big challenge. The energy of a proton at the LHC is about the energy, the kinetic energy of motion of a mosquito buzzing around. Now that doesn't seem very much, but you've got to remember that a mosquito has in it something like 1,000 billion protons. So it's as if the mosquito, which is made of these 1,000 billion protons, its energy was suddenly concentrated on one of them. So it's a huge amount of energy.
What's been going on at CERN in the last several years is smashing the particles together at higher and higher energies, creating higher and higher temperatures. Temperatures that are the equivalent of millions of degrees, far hotter than anything in the universe today, hotter than anything that has existed since the first millionth of a second. Now, it might be surprising if I say, and those temperatures are actually extremely cold compared to where we want to go to next, where we think that something interesting happens. In a sense, all that we have done so far at CERN is seen the universe when it was frozen like this. What we want to do next is to be able to melt the universe, if you like, turn the ice into real water.
And what happens when the universe melts? The holy grail for particle physicists, and the reason they're spending billions on this experiment, is to try to answer a simple but profound question. Where does mass come from? A question you might have thought they'd have figured out by now.
One particular thing we're looking for is something called the Higgs boson, which is associated with the mechanism by which particles acquire mass. We're in a very peculiar position that we know a lot of so-called elementary particles. We can organize them into certain families. As we go deeper, the structure seems to be becoming simpler. But they have a very diverse range of masses. Some are very light, even massless. Some are heavier. And we don't understand the mechanism by which they get different masses. We have on paper theories of how particles get mass, and they predict the existence of new particles called Higgs bosons, but we've never found one. We're pretty sure it exists, but it's a generic idea. It could take different forms, and it's a roadblock, actually, to understanding more deeply the structure of matter, is to try to find out this Higgs boson or bosons and what it or they are and how they operate. It will unblock progress. I mean, we know something is hiding the fact that all particles are trying to be massless and generating mass for some but not others. And until we know the answer to that, we can't get deeper into the structure of things.
If they discover the Higgs boson, it will be one of the most exciting scientific developments of the new millennium.
But what if they don't find it?
Whether there will be a Higgs particle or something more subtle along the same lines is not yet known. But if nothing at all showed up, then that might be even more interesting in a paradoxical sense, because it would say that there is something fundamentally flawed somewhere in our present understanding of either relativity or quantum theory, the other great, quote, laws as we believe them to be. So it would be a signal that there is something missing, and exactly whether that would be a profound re-evaluation of all of science or whether it would be a small thing somewhere to be cooked up, who knows?
Scientists have theories for the secrets they'll discover inside atomic particles, although they can't be sure what's there. But whatever they do discover, scientists assume that the laws of conservation will still work, even at the smallest scale.
Certainly, when one gets the results and one analyzes the results, there are conservation laws which must be strictly satisfied. So when one says one gets the results right, these are the basic things which must be right. So we could not have something happening which is violating one of the cherished conservation laws.
Every law has to be continuously tested and try out the domain of validity. And sometimes we found, it was only approximate, it works here. But when we really push things to very extreme energies or very extreme temperatures, the law doesn't work anymore. So I think I would be very surprised if energy and momentum conservation changed, but it's possible.
The particle physicists should have a smashing time with their new collider. Whatever the outcome, the laws of conservation of energy and momentum will have played their part. Even if radical new laws are discovered, it's a pretty safe bet that nature will remain conservative with a small c.